I'm here to present to you how the Randall encryption algorithm works. Randall has been selected by the National Institute for Standards and Technology in 2001 to be the new advanced encryption standard. Before that, the data encryption standard was the standard encryption algorithm that can be used to encrypt bulks of data. So let's have a look on how the Randall or the AES work. Basically, you have a plain text and a cipher key or an encryption key. This is what you want to encrypt, and this is the key that is going to help you encrypt or protect your data. Those two are going to be passed to your encryption algorithm as an input, and both of them will be used by the Randall encryption algorithm to produce your corresponding ciphertext, which is basically the protected version of your plain text. Let's have a look into how the encryption algorithm really work. First of all, you are going to have your input. The input can be anything. It can be text, can be a video, it can be an audio file. It doesn't matter. But eventually, it's going to be represented in binary or in hexadecimal for simplicity. And that input is going to be divided into blocks of 16 bytes. Each block equals exactly 16 bytes. The first 16 byte is going to be copied into the state matrix, just like this one. And that state matrix will go through the AES encryption or the Randall encryption to produce the corresponding ciphertext. Also, we are going to have an encryption key. The encryption key can be 16 bytes, 24 bytes, or 32 bytes. But for this demonstration, we will assume that the encryption key is 128 bits, which is equivalent to 16 bytes. Those 16 bytes will be passed to what we call a key schedule. And the key schedule is an algorithm that will be responsible for expanding your encryption key to generate enough number of round keys that will be used by the Randall encryption algorithm. All these details will be explained in the upcoming slides. So now we will pay attention to how the state is going to be processed by the Randall encryption algorithm. Let's have a look. This is basically how the encryption algorithm works. As you can see here, this is the state matrix that has been copied from the previous slides. We will use the encryption key, the actual encryption key, we sometimes call it the master key, to do a first add round key transformation. And this transformation is called key whitening, or basically whitening. Then the input after the whitening stage will go through 9 different rounds. Each one of those rounds will have those 4 transformations: subbytes, shift rows, mixed columns, and add round key. And as you can see here, in every add round key transformation, we are using a different key. These are 9 identical rounds. The only thing that differs is the round key in this, basically the add round key transformation. The last round will basically contain the 3 other transformations: subbyte, shift rows, add round key, but the mixed columns is not going to be there. So this is basically how the encryption algorithm works. Now we know how AES work, but to have a better understanding for the real encryption algorithm performed by the real encryption transformations performed by the Randall, we need to know how those internal transformations really work. So let's have a look at the first transformation. And here I'm talking about the subbyte. First of all, we will use this substitution box. It's a static entity that has been suggested by the Randall encryption algorithm designers. And this is your state matrix. For each byte, you will take the first 4 bits, which is going to be, because we are representing things in hexadecimal here. So the first 4 bits will be equivalent to the hexadecimal 1, and the remaining 4 bits will be equivalent to the hexadecimal 9. So 1 and 9 will serve as indices for the S box. For example, we will go for row 1 and column 9, like this. Row 1 and column 9. In the intersection between row 1, column 9, we will see a value there, which is D4. That value is going to replace 1, 9. And the same is going to be done for the other values as well. For example, this value, row 3, column D. So we'll basically replace it with 27, as you can see here, and the same will be for the other values as well. This is how the sub-byte transformation work. Now let's have a look at the other transformation, which is shift rows transformation. In shift rows transformation, the first row is going to remain as it is, but the second row is going to be rotated to left by 1 byte. The second row is going to be rotated by 2 positions, and the last row will be rotated to left by 3 positions. And this is how shift rows will operate. And last but not least, we will see the mixed columns transformation. In the mixed columns transformation, we will use a static matrix, this one, with the same values all the time. And this matrix is going to be used to it's going to be multiplied in this column. So for example, to get the first value here, we will multiply the first row in this column. And we know that the multiplication of the matrices is going to basically get a value or calculate a value based on all those values and all those values, right? To just have the value of the first output in the state matrix after the mixed columns transformation, right? And we will repeat the same for all the other columns to have the state matrix after the mixed columns transformation. The last transformation, as I mentioned, it will be repeated for the other columns as well. Now let's have a look at the last transformation, which is a straightforward transformation, the add round key. We will get the state matrix and we will get the corresponding round key, and we will carry an XOR transformation between the state matrix and the round key. So simply XOR this value with this value, and the result is going to be the output of basically the add round key transformation for that byte. The same is going to be done for all these bytes and for all the remaining bytes as well. So this is how the internal transformations of each round work. And by knowing that, now we can say that we really know how AES work. To assess your knowledge, I have a Kahoot here. Let's use it together. I'm going to call my name, for example, Abdul Rahman. So what is the block size of the AES? As we mentioned, the block size is 16 bytes or 128 bits. So yes, that is correct. Let's move forward. AES uses 4 transformations to do the encryption. Correct. True. And those transformations are the add round key, by substitution, uh, row shifting, and mixed columns. The blah blah is responsible for expanding the key. It's basically the key schedule, right? The algorithm responsible for expanding your key is not the key expander, by the way, it's the key schedule. The component used to carry the sub-bytes transformation is called the substitution box, or for short, S box. That's correct. Okay, move forward. AES encryption starts with add round key transformation and ended with mixed columns transformation. No, this is false. If you remember, the transformations, as you can see here, it starts with sub-byte and ends with add round key in each round, right? So This is my presentation. I hope that you enjoyed it, and I'm looking forward to see you in the class.